Okay, let's look at Pentium Pro translation. So Pentium Pro generate 32-bit virtual address and using page table or TLB they translate to physical address. And we can classify this with 4 different cases. Let's look at case by case. The first case is the page tables and page are both present in main memory. Okay? So you can do the translation, and also there will be no page miss. So in general, you can do the translation through the TLB if you access the page before, and if you still cache the entry, page table entry in the TLB. But if you miss, you can ask the operating system to find the page table entry for the translation. And operating system, from the virtual page number, the first 10 MSB tells you the location of page directory entry, because you don't know whether the page table page is in disk drive or in main memory, because initially you wrote this page directory. So you have page directory in main memory, but you are not sure about page table or actual page. So in this case, page table, the page is actually page table is in main memory. So you can find page table entry from the main memory stack tab. 뭐 하나?
받고 있었어요.
PPT? 이거 봐 그냥. Anyway, so you find page table entry, you insert into the TLB, and you can do the translation. And then page is also present in main memory, so you have a TLB hit and page hit. Okay, so you access the cache. Cache will be a miss if you never accessed the page before. So if you miss, you go to main memory and you find data from memory. Okay. So in this case, with TLB, you can avoid this OS action. So there will be no movement from disk to main memory, because both page table and data page are in main memory. Okay, let's look at the second case where page tables are in main memory but actual page is missing, so actual data page is in disk drive. Okay, so in this case you can do that translation either through TLB or through the help of operating system. So you find translation, you do the translation, but page table entry, the TLB said the present bit is 0, which means page is missing in the main memory. So you need operating system help. So OS generates page fault and move this data page into main memory, and you can continue. And next time you execute the same instruction, it will be a page hit. Okay, so you can access the page from the main memory. So in this case, page fault or page miss exception occurred, and the handler receive this information from this exception and then move this data page from disk drive to main memory. So they always move instruction or data from disk drive to main memory on a page by page basis. Okay, it's called demand paging. Demand paging means on a miss they move, they do not move beforehand. Okay. The third case is okay, this is the continuation of the second case. So in general, OS action is whenever there is an exception, they need to check whether the address is legal, because address sometimes can refer to some invalid address. in general, it codes segmentation violation. Okay, we look at how this invalid address can be generated in the rest of this slide. So if it's legal address, then it leads page table entry and find free page from the page frame main memory and lead the data page into main memory and so on. So the third case is page table missing but page present, which means the data page is in main memory but actual translation you cannot do the translation, and this had some consistency issue. Because if you move this page out, you need to update this page table, but this requires moving this page table page into the main memory, and this is somewhat complicated in general. So in general, you prefer at least translation information is in main memory, right? Compared to actual instructional data page. In this case, the other way around. So you cannot do the translation, so this is useless. Okay? So in Linux or Unix, they disallowed this situation. And if a page table is swept out, which means if you don't have translation information, you also swap out. Swap out means you move this to disk space. Whenever the page table is not present, you also swap out disk data or instruction page also. Okay, so the translation information always has precedence or priority over actual instructional data page because it's useless without translation information. Okay, and the final case is both page table and page is missing. So it generates translation page table entry miss in main memory. So you have to move page table page into main memory first, and then it will generate page miss. So you have to move disk page into main memory and so on. Okay. And Pentium Pro also use virtually indexed, physically tagged cache, which means from the virtual address, if you can extract index from this page offset, then you can access TLB and cache in parallel, because at least you can do the index decoding for the cache access. So you can accelerate TLB and cache access by doing it parallel. Right? If you do it serially, it takes one cycle for TLB and another cycle for cache access. So at least two cycles, but if you can do it in parallel, maybe you can complete it within a single cycle. Okay? The same principle applies to Pentium Pro. As I said, for first level cache, it's quite small. So you can extract the index from the page offset most of the time. Okay? So you can access TLB and cache in parallel and speed up the cache access. So here, it doesn't show the details. Let's look at, okay, here. So for cache, actually index is 7-bit. The cache structure for first level cache for Pentium Pro is, do they have here? Okay, let's go back. Arrow instruction cache and data cache is 16 kilobyte and 32 byte block and 128 set. Okay, and 4A set associative. So 128 set means you need 7-bit for index, and 32 byte block means you need 5-bit for block offset. So for index decoding, the page size, if the page size at least 4 kilobytes or bigger, then you can extract index from the page offset directly. Okay? It's quite easy, right? So page size is 4 kilobyte at least. So you can choose either 4 kilobyte or 4 megabyte. So page offset is 12 bit. So out of 12 bit, you can extract this index. So you can access the cache in parallel with TLB access. And you can do it in parallel. Okay? Okay. So we finish up hardware part. Let's go to the operating system view of virtual memory more. Linux organized virtual memory as a collection of areas. So area, you can view them as a segment. So maybe the text segment or global data segment or BSS segment and so on section. Okay. So what is area? So you have a collection, a set of areas. An area is a contiguous chunk of virtual memory whose pages are related. So contiguous means area is consecutive locations in virtual address space that are related. So area may contain multiple pages because area can be bigger. So example of this area can be code segment, instructions, or data segment, data, right? Or heap, or shared library segment, and so on. Okay. So any virtual page should be contained in some area. Okay. So it should be. It sounds like apparent, but it means that it's a virtual memory is a collection of area. So you view virtual memory as just linear array of bytes, right? But there can be holes because some addresses are not mapped to some segment. Okay, so you can view them as a set of areas. Area is contiguous, consecutive locations, but in between there might be holes that are not mapped to any segment. Okay, so if you access their location, it means invalid address. Okay. So the virtual address space can have gaps. Gap means these holes. Okay. The kernel does not keep track of virtual pages that do not exist. So you can view them as a set of pages or set of areas. Okay. Area is a bigger chunk. Area can be a set of consecutive pages, but in between these areas there might be gaps, holes, and in these holes there are still some address, but these are invalid address, and you don't have to maintain information, translation information, because it's empty. It's not mapped area. So kernel does not keep track of virtual pages that do not exist. So these are areas. So there are some holes. So this is not used. Okay, and you have text area and data area, another hole, and shared library area, another hole, maybe stack and so on. Okay, so there are some holes, gaps, and the kernel maintains some task structure for each process. So for each running program, kernel maintains a data structure called task structure. It contains all the information the kernel needs to run this process. Okay, so for each process, it has some data structure that's required for that process. It contains process ID, what's the identification number, and pointer to the user stack, and the name of the executable object file. Okay, so from the same Internet Explorer file, you can create different processes. Each process is independent, but they are referring to the same executable file. And program counter. Each process, the current program counter is different, right? And it also contains this main memory structure inside this task structure. So one of these entries in the task structure characterizes current state of virtual memory. So this is some substructure in the task structure that's related with virtual memory. And in here it has the PGD, which is the base address of the page directory table. Remember, if you want to execute some process, you have to load the page directory first into the main memory, and this has a pointer to the page directory so that you can load the page directory into the main memory. And another pointer which points to a list of virtual memory area structure. So this is actually this area, and this is a pointer, so this is a linked list of areas. Okay, let's look at visually. So you have task structure, there is a process ID and other information, maybe program counter and so on, priority and so on, and you have a another substructure called which point to this substructure called structure, and one of the entries is page directory address, and another entry is a pointer to a linked list. Okay, each of this virtual memory area structure has information about each area. Okay, linked list. So what does it have? The start address of this area, the end address, and the protection information. Protection information means whether this area is readable, writable, executable, and so on. And this also has flag information. Flag means what kind of this area. Area can be a shared or private or anonymous, 3 different types. And it has a pointer to the next area. So this is a singular linked list. Okay, linked list. Okay, page fault handling. So as I said, on an exception such as page miss or TLB miss, the Linux first check whether the address is legal address before they actually find page table entry or actually find the disk address for that instruction, for that address. And this legal address means this address is in an area defined by virtual memory area structure, which means the address should belong to any of these areas that are mapped. If the address is referring these holes, then it means invalid address. Okay, then you have segmentation violation. Okay, or you are accessing other space, then it causes segmentation violation. Anyway. Okay, so in this case, you are trying to read some area which is not mapped to any. You are referring to an address which is not mapped to any area. So this means this is an illegal address. So you generate segmentation violation. Okay. And number 2 case is you are trying to do a write in the code segment, right? Code segment. But usually code segment, if you look at the protection information, this is read only. But you are trying to do a write. So it generates protection violation or access violation. Okay? Because you are trying to modify the instruction which is only read only. Okay? So it generates exception and this process will be terminated because it's doing illegal operation. Number 3, you are trying to read some global, this is static data segment. You remember, you store global variable and all the static variables in this segment. And you're trying to read some data which is allowed. So you can continue. And if this is a page miss, then you have to handle the page miss. You bring the disk page into the main memory. Okay? Okay. So Linux, and this includes Unix, initialize the content of virtual memory area by associating with an object on disk. Okay? So each of these areas are associated or mapped to some object. Object may be a executable file. Okay? File. So when you start to learn, you actually initialize the content of virtual memory area by associating with an object on disk. So in general, you create a new virtual memory area structure and page table for area. So by mapping means you create an area and you associate this area with some file. Okay? And that's all. But when you actually reference that page, actually the initial content will be loaded from the disk drive, because you map that area to the disk file. Okay? And areas can be mapped to one of two types of the object. One is regular file, such as executable object file. The other is anonymous file. Okay? The regular file on disk, the file is divided into page size pieces. So if you have an executable file, it will be divided into page sizes. Okay? Because you move page by page basis. And initial content of each page comes from each actual page, disk page on the executable file. Okay? And if the area is larger than the actual associated file, then the remaining area is padded with zeros. Okay? So you create some area and you map some file, but area is bigger, then you map entire file, but if there are some remaining things, you pad with zeros. But normally it's the same size. Okay? And anonymous file means this is for BSS section. BS section is global variable, but not initialized. Okay? And you don't have to, you just put placeholder at the executable file, because you know the initial values. You don't want to create a space for that, right? And you don't want to duplicate. But when you actually load the program, and you actually learn, you create that BSS section. But BSS sections are initialized to zeros at load time or run time, right? For this case, you use this anonymous file, which means it's a file, but it's actually initialized to zeros. Okay? And an area can be mapped to an anonymous file created by the kernel. The initial content of these pages are initialized at zeros, because these are global variable, uninitialized, and you initialize on demand by zeros. So they use the same convention. They regard them as file, but they call them anonymous file. But these are means they just initialize to zeros. Okay, and these are called demand zero pages. On demand, they initialize to zeros. Okay, and so you can map some virtual memory area to a file, either regular file or anonymous file, but no virtual page are copied into physical memory until they are referenced. You just map. But when you actually reference, you copy from either executable file or from anonymous file, just initialize to zeros, on demand. And this is called demand paging. And this is crucial for time and space efficiency. So you can map using this system call mmap. You map. So the meaning of this procedure is map length number of bytes starting at offset of the file. This is file descriptor specified by FD. So you have some executable file starting from this address, you map to this address, to virtual address in this space. And virtual address, this is start address, and this is the length. Starting from this address, this size, you map to some file starting at this offset. Okay? Stack top. Understand? 어려운 거 없는 거야. 그냥 매핑하는 거야. You have a disk space. Okay? You have code segment. You want to map to some executable file. Right? So code segment starting at this address, the size, you know, right? So you map this amount of area, you create this area by mapping to some executable file, code segment. Okay? And this is mapping to code segment. And at the same time, you provide this protection information and flag information. Protection, executable, readable, writable. So it's either 1 or 0. Right? You need 3 bits. Okay? And flag means there are 3 different flag. There can be 3 different area. One is private, shared, or anonymous. Shared means it's the shared object. So some area might be mapped to some file, but this file is shared by different process. So it's totally shared. If you read, even though it's mapped to different virtual address space, it's just shared object. If you write, and it's visible to another process. Okay? It's shared. Private means this indicates private copy and write object. So you map to a file. So both of them are mapped to the same file, but if you declare as private, then if you do not write, if you just read only, it's same as shared. But if you do a write, if you want to do a write, you have to do a write in a private space because you don't want to disturb other people. So this is called private object. We'll see some figure example. And anonymous means this demand 0 pages. And it returns a pointer to the mapped area. And you can unmap, which means you can map, create a virtual area. You can delete the area by unmap. Delete the area starting at virtual address. Okay. Let's look at this shared object. Why shared object? Many processes need to share identical read-only text areas, as we have discussed previously. Each T shell, this is a shell. Shell means it's command line interpreter in Linux. It's like prompt, and you type the command and enter. Okay. Each T shell, so you can initiate another shell command in every window, but every T shell have the same text area you want to share, okay? Because this same text area is read-only, okay? And standard library functions such as printf is also shared by different process, and it's usually read-only, right? It's totally shared. So you want to share this object. If you don't share, every executable file has separate copy of printf, which means the disk space will be wasted because you have redundant copy of printf, scanf, and also main memory you have a waste. Okay, and it's amplified because process can come from multiple process can be created from a single executable file. Okay, and because you don't want this duplication. So an object can be mapped as either shared object or private object. Shared object means any write to that area is visible to any other process that have also mapped the shared object. Okay, so if you have a process 1, okay, Internet Explorer, 경선, okay, Oksana, PowerPoint, okay, both of them have printf, here's printf, okay, you can share this object, you can map this object into your virtual address space in some area, okay, and it's shared. It's shared, and sometimes printf can be upgraded by maybe by the operating system people or library people, right? We have updated version of printf, and it will be visible to both process. And if you modify this to update, and it will be visible to the other process. It's totally shared. Okay, that's the shared object. And virtual memory area into which a shared object is mapped is called the shared area. So if you have a virtual address space, some area, there is shared object, this is called shared area. Okay, shared area. Private object is somewhat it's some kind of sharing, but it's private. Okay? Any write to that area is not visible to other process. It's private. So if you map to a same file, but you declare as private, which means you are sharing, but if you to write, you have to write in your own space because you don't want to disturb other process. It's shared, but it's private. Okay? So the change shall not reflect the object on disk. Private objects are mapped into virtual memory using copy on write policy. Copy on write policy means first, if you declare this file, this object as private area, then you can share, you can map, the initial content will be the same. But if you are doing a write, then this copy on write policy will be active, which means initially only one copy of private object is stored in physical memory, but and the page table entries for the private area are flagged as read-only because you are mapping to the same file. You only create a single image on the main memory. Okay, only one copy, but you mark them as read-only and private. Okay, read-only. So any write to this private area triggers protection violation because you are doing a write on a read-only. You mark them as read-only because it's private. Then the handler needs to create a new copy of the page in physical memory, this page by page basis, and restore the write permission to the page. So if you do a write, if you want to do a write, you need to create a new page and modify read-only to read-writable, and you create your own copy here. But it will not affect the other process. That means private. Okay. After the handler returns, the process proceeds normally. So shared object. Let's go back to shared object. One process, they map this file into their area, and this is shared area. And when you access this page, you actually move this page into physical memory. There is only one copy, right? And if you map in process B, they map in different address space, but same shared object in shared area, then you don't have to copy a new page to main memory because you have a shared copy already. So you can use this image directly from the main memory. So you share a single image in the main memory and single file on the disk drive also. This is totally shared. So if you do a write, then it's visible to the other process. Okay? This is shared object. Private object means initially they declare them private, but they are mapping to the same object, but they declare them as private. Okay? So they have only a single copy. Because this is created from the same object, you don't have to copy the new one, right? You can use the existing one. As long as you are doing a read-only, right? Read-only. Read-only means you don't have to copy a new one. You can use the existing one in main memory. But if you trying to do a write to this shared object, then this will generate protection violation because you are this is marked as read-only. So in this case, the handler creates a new page and you use copy and write policy, which means you have to copy on your own, and it's not so you should not write into this shared image. You have to create a new physical memory page and you have to write into your own private copy. Okay? And this process will not be affected by this write because it is doing a write its own copy in its own separate page. 알겠죠? Okay? Okay. So it's not actually revisiting the actual order in the textbook which we discuss exceptional control flow, and then we go to this virtual memory. But we are going the other way around. We first discuss virtual memory, and then we will discuss exceptional control flow, which is the next topic after this virtual memory. So there is a system called EXEC, which means you can learn a new program in the current process. So you are Internet Explorer, you are learning Internet Explorer. In your process, if you run this EXEC, you can learn PowerPoint. Okay? You load another image, executable file into your process, and you become PowerPoint. That's possible. Okay? Because okay, I'm not going to detail. Anyway, this is called EXEC. So to run a new program in your process, for all the areas, you have to free all virtual memory area structure and page table. So there is an existing collection of areas for that Internet Explorer. So you have to delete, unmap, right? You have to delete all the areas and also delete page table entries. You don't need translation because you are learning different program. And then you have to create a new virtual memory area and page table for this new program. And for this new program, you have stack, BSS, data, text, and shared library areas or segments. Okay? And usually text and data segments or areas are backed by ELF executable object file, which means you map text area and data area to a file, PowerPoint file, which is in the disk drive. Okay? And BSS and stack are initialized zero, which means anonymous file, and these are demand zero pages. On demand, if you create a new stack frame, you create a new page, and those pages are all initialized to zeros. Okay? And BSS, global uninitialized variables, these segments will be initialized zero if you reference that address. And set program counter to entry point in the executable. So if you have executable file, there is a symbol which tells you the start address of your program. And so you set program counter, and then maybe before you run this program, you have to load the page directory into the main memory, and you set your program counter, and then processor will fetch the instruction starting from the start address. And this will generate TLB miss and page table entry miss. It will bring page table pages, and essentially it will generate page miss. So it will generate instruction and data into main memory. Okay? This is how a new program is learning. Okay? 알겠죠? Because in Linux or Unix or any operating system, a new process is created as a child of an existing process. Okay? So we'll discuss this later, but initially there is a process called init. Okay. This is some ancestor of all the other process. Okay? It starts, init creates maybe TTY, console process, terminal process, and inside terminal process, you create shell process, T shell or C shell process. In T shell, C shell process, you can run some program or you can run the command, and then this T shell process creates a child process, and in the child process, actually, whenever a process creates a child process, child has inherit all the executable image, same as the parent process. But by learning this EXEC, it can learn PowerPoint or other programs. Okay? So if you actually if you want to start a new program, you have to learn EXEC. Okay? And what EXEC does is it creates this area by using the map function, mmap function. You map text and data to executable file, other area to unidentified file, demand your pages. You set program counter, you load into page directory, and then start. 알겠죠? Understood? So fork revision, I haven't explained this fork before, right? So fork is creating a new process. So a process can create a new process by calling this system called fork. So when you actually create a new process using a fork, you copy the old process or parent process, all this image. So they copy old process, parent process, this virtual memory structure and page tables. So if this parent process creates a child process, at the creation point, the child is exactly same as parent, right? It's same as parent, but it's independent process. 아키텍처 하다가 OS로 넘어가니까 조금 컨텍스트가 달라서 어렵죠? 조금 딱딱한데. In computer, a parent creates a child. Child is exactly same as parent. Exactly same. Same image, same program counter. Same. But starting from there, it can be different. We look at how this process and fork mechanism is handled in the operating system in the next topic. Compared to computer, humans, when your parent creates, you inherit your DNA, half of them from your father, half of them your mother. Right? So it's quite different. 그렇죠? Okay. So after the creation point, the two process, parent and child, are sharing all of their pages. And how to get separate spaces without copying all the virtual pages from one space to another? They use copy and write technique. So when you create a child process, you don't have to create a new page. You can share. But this is copy and write, private. Okay, you have the same image, so you don't have to you don't have to move any disk page into your main memory because most of them are in main memory from the parent process. So you can share, but you are using copy and write policy because it's different, independent process. If you do some other operation to a write, you have to create your own copy, and then parent-child will diverge. Okay, initially it's exactly the same. Okay. So writable areas, they mark them read-only, and this is actually private copy and write object. So write by either parent or child will generate protection violation, and you create your own copy and doing a write. So they are separate. Okay. And these copies are default until absolutely necessary. Right? So when one of this process tries to modify a shared page, then they do a copy and they have their private copy. Otherwise, they are exactly the same. Okay? Okay, so let's discuss heap. So we know what is stack, right? Stack frame. And we discuss text segment and PSS and data segment and so on. But heap, let's discuss more. Heap. And it's called dynamic memory allocation. A heap is an area of demand zero memory that begins immediately after the PSS area. So if you look at memory map, you have text, data, BSS, and then you have heap. And so the example is you can use malloc and free. Right? Malloc is asking the system to allocate this much space. So system should have some allocator. And this allocator maintains the heap as a collection of various size blocks. Okay? So whenever you do a malloc, you request this much space, right? And each space can be variable size. Okay? So heap is a collection of various sized blocks, and each block is a contiguous chunk of virtual memory that is either allocated or free. Okay? So maybe starting at to have the so this is reserved, not used, and text, data, BSS, and this is heap. Okay? On the top it's pointed by BRK pointer in the operating system, and this is for the shared region, shared object, and this is the stack, and this is corner part. We are discussing this heap. So we start from right after this BSS area or BSS segment. So maybe starting from here, let's say this is for heap area. This is the end of BSS. So when I request, let's say when I request this much, when I do malloc, maybe 1, another malloc 2, another malloc 3, and so on. So it's variable size. But I can also free. I used that object, and I don't need the space, so I can free this second object. And this can be a free block. Okay, this is allocated block, and so. Okay. So this is on demand. I use only this much, and after I use, I reclaim. I return that to the system. So in this allocator, there are two different schemes depending on the programming language. Okay. In C, we use explicit allocator, which means the programmer actually determines the allocation and free. Okay, so the application, the program actually allocate and free space by itself. So in a C program, you do malloc and you have to be responsible for free, right? Otherwise, if you do malloc and you never free, then it will be garbage. And it will occupy the system memory. Eventually, it will grow if you run the program more and more. If you malloc and again, and then it can actually cause the system to stop, because your systems are filled with this garbage. But the programmer is responsible for allocation and free. Okay. The other scheme is called explicit allocator. The other scheme is called implicit allocator, which means the application or the programmer is responsible for allocation, but it's not responsible for free. Okay. You just request, and you don't care about free because the system maintains this free space. Okay. And this is used for Java or functional language such as Lisp. And so the allocator, the system, needs to detect when the allocate block is no longer being used. If some block is not used, then you have to return that to the system automatically. And this is called garbage collector. And this process is called garbage collection. So in this language, you need some system should support this garbage collection. Otherwise, there will be too many garbage, and it will slow down the process. Eventually, it will kill the, suspend the process. Okay. So this is heap. Let's look at this malloc package. So this is in standard library. So you can do malloc and this much size. If this is successful, the system will return the pointer to a memory block of this size byte. So you allocate this much bytes, and if there is a space, the system will return this much, allocate that much space, and it will return the pointer to that area block. Okay? And when the system allocates, they are aligned to 8-byte boundary. So even if you want to allocate 9 bytes, you request 9 byte allocation, such as malloc, then it will allocate 16 bytes, multiple of 8 bytes, because 8 byte, it can contain any kind of object, because the biggest object in 32-bit processor, 8 byte means double precision floating point number. Okay? That's 8 byte. And if you cannot allocate, or size is 0, then it returns null. Okay? If it's unsuccessful, if the request memory is bigger than the virtual memory, then it returns null and set error number. Okay? So if you request size 0, it returns null. If it's unsuccessful, it returns null, but with this error number. And there is malloc, and there is realloc, and there is calloc. The difference between malloc and calloc, you request this much size, but initialize. You don't care. But if you want to initialize to 0, then you have to use calloc. Calloc means it will be initialized to 0. Okay? Inside this malloc, they use this mmap function, which we have discussed. Okay? So maybe, or sbrk function. Realloc means after the allocation, you can change the size of the object. Okay? So you can increase or decrease the size, and you can use realloc. So change the size of the block pointed by P, and return the pointer to the new block. And if you increase the existing block, the content will remain the same. Okay? If you decrease, then you remove, but the smaller size, the content should be the same. That's the meaning of this sentence. Free means after the allocation, because in a C program you are responsible for malloc allocation and also free. So you have to free, and you can, if you free, it returns the block pointed by P to a pool of available memory, which means it was allocated block, but after free it becomes free block. So the system can allocate the free space to other malloc. Okay? After free. Okay? And this P must come from previous call to malloc or which means malloc and free should be one-to-one correspondence. If you do a free to some arbitrary space, then it means error, right? You allocate and then you can free, but if you don't allocate, you cannot free. Okay. Let's look at this code example. So here it allocate request integer. So if integer is 4 byte for 32-bit processor, this means 4 n byte allocation. Okay? So it asks allocate n integers here. If it's null, which means it cannot allocate, something wrong, and generate some error message. Otherwise, you're successful. You allocate n integers in the heap area. And then, since you allocate n integer, and that address is pointed by a P, starting from 0, you initialize this new integer, n integer with I. So n integer 0, 1, 2, 3, and the final should be n minus 1. Okay? Initialize. And then sometimes you want to increase the size. So you realloc and you increase from n to n plus m. Okay? Using the realloc function. If it's null, it means you cannot do. So error message, otherwise you are successful. And for new entries from n plus n to n plus n minus 1, you initialize with another value. So you create 100, so 0 to 99, and another 100, 100 to 199, initialize. Okay? So now you, in the system, you have a block of n plus m integers, and then you print these values on your screen, and then free entire n plus m integer. Okay? So very simple example. Okay, let's look at the allocation example. You do a malloc, so starting, this is a heap area. This can be an integer, so maybe 4 integer. Malloc, so contiguous space, you allocate 5 more integer. Malloc, 6 integer, you free. So this becomes free blocks. Free block. You malloc 2, so free block. So you always start here, you can allocate here. Okay? So let's look at the requirement for the system, the allocator, explicit allocator, what it should do. From the application side, application can issue arbitrary sequence of allocate and free. It can request, I request this much, I free, request, and so on. As long as allocation and free, there should be one-to-one correspondence. Otherwise, it means there might be a garbage. All right? To the allocator, it cannot control the number or the size of allocate block because it's controlled by the programmer. It's programmer's responsibility. They request this much. Okay? They can request arbitrary sequence of allocation. Okay? But the allocator side is some passive. If you request, I should allocate. Okay? If you free, I should free. And the allocator must respond immediately to all allocation requests. So they cannot reorder buffer request or buffer request. They ask, I allocate 3, 105, and if the system cannot reorder this order, they have to do it in sequence. Okay, 3, 5, 100, and so on. And they should allocate blocks from free memory. That should be obvious, right? If it's allocated, you cannot allocate. And must align so that they satisfy all align requirement. So in GNU library on Linux, whenever you request this much allocation, they allocate 8-byte boundaries, which means at least multiple of 8 bytes. Okay? And so, but the system can manipulate or modify free space. Free space is so for the free space, they can organize free space, and how you allocate, okay? How you use this free space is up to the system, right? There are multiple free space. If the system, the programmer asks this much space, I can assign that free space or the other free space up to the system, okay? And the system cannot move the allocate block once they are allocated. So after they allocate and free, but there might be holes, right? Unused block, there might be fragments, and system cannot reorder and compact this hold together because the system is passive in this system. So compaction is not allowed in the explicit allocator. So it's all up to the programmer or application. Okay? So the goal of this allocator in this system is you want to maximize the throughput, which means throughput means number of complete requests per unit time. If there are 5,000 malloc and 5,000 free in 10 seconds, the throughput might be, this is 10,000 malloc and free in 10 seconds. So it's about 1,000 operations per second. That's the throughput. And if the system is slow, that's bad. So you want to improve the throughput, right? From the system perspective. And you also need to maximize memory utilization. So you want to minimize fragmentation. But if you want to minimize fragmentation, it may slow down the throughput. So there is a trade-off. Okay? And usually similar objects should be allocated close in space because there are some locality. Okay? So if the user is asking some similar object, then it should allocate in the near space. So let's look at the fragmentation. There are two types of fragmentation. So internal and external fragmentation. And the example of internal fragmentation is for the page. So page is a fixed size block, right? Operating system page means if you use 4 kilobyte page, any disk movement from main memory should be on a page by page basis. So even if your programs are less than a page, you have to move a page, right? Which means there are some unused portion in the page, which are called internal fragmentation. Okay? Let's say your program is 졸린가? 다 졸고 있어. Your program is, let's say, 7 kilobyte. Page size is 4 kilobyte. Then your program can fit in 2 pages, right? But the second page, there is a 1 kilobyte fragmentation hold, right? Because you do not use the entire space. You use only 3 kilobyte out of 4 kilobyte. So that becomes the internal fragmentation. Okay? 어렵진 않은데 졸립지 좀. 그쵸? 어려워? Normally, the computer architecture class does not include this much content, but this is filling the gap between computer architecture and operating system. Because operating system does not discuss this much detail usually, so I'm trying to fill the gap. Okay? So in this class, I'm covering computer architecture and in between this operating system and in between. Okay? And external fragmentation can be caused from the heap. Okay, let's look at the external fragmentation example. You request 4 using malloc, 5 and 6, and you free the second block, P2. So this is free and this is free and this is entire. You ask for 6, but there is no contiguous chunk of 6 size block in the heap, even though the total free space is greater than 6, and this is called external fragmentation. Okay? And what should you do? You should do compaction. Compaction means you move this here and create a bigger hole so that you can accommodate new requests. That's called compaction. So for the allocator, there are some implementation issues. Free block organization. So if you want to do allocation, you have to organize your free blocks so that you have to know which space I have to allocate and how to organize this free block and how do we know the size of free block. Okay, how do we keep track of this free block? This is an issue. Okay, and placement means how do we choose an appropriate free block for a new allocation? You request for 7, and there are size of 9, there are size of 10, and so on. Which one would you allocate for this request? That's the placement policy. Okay, you can use any free block that's bigger than this request, Splitting means sometimes there is a free block of 10 and you request 7, so you allocate 7 and there are remaining 3. This becomes another free block, and this is called splitting. So one become allocated block and the other fragment become free blocks. Coalescing means sometimes you have 2 allocated, you have 5 allocated, and so on. But you free this space, and you free this space. If you free without any extra things, then you have free block of 2, free block of 3, but these are adjacent. So what you can do is you can combine these 2 in a single free block. This is called coalescing. Okay, this kind of operation should be handled in the system allocation. Okay, and to do that, we need to maintain some information, and we use this kind of header. We should at least know the size of this block, and we should know at least whether this block is allocated block or free block. Okay, this information can be encoded in 4 byte in a single word. Because the block size is a multiple of 8 bytes, we don't have to use this LSB 3-bit, and block size can be specified by upper 29 bits, right? Because it's multiple of 8 bytes. And using this 3-bit, you can use this LSB as its allocation or free. So if it's 1, then it's allocated block. If it's 0, then it's free block. So actual block shape is like this. This is actual data. It's called payload. Okay? So if you request 100 integer, payload means 400 bytes. Right? So this block can contain 100 integer, 400 bytes. But at the beginning, you have this header, which has the size information, block size. This is 400 byte block, and also this is allocated block. You have to mark them allocated. And sometimes you need padding, right? Because this should be multiple of 8 bytes. Okay? And malloc returns a pointer to this pointer, which is pointer to the beginning of the payload. Because you actually, from here, you can initialize contents from 0, 1, 2, 3, and 1 from 99, right? And actually the block size is the entire block size, not this size, okay? And this is marked as 1, okay? And 400 bytes, maybe 4 bytes, and another 4 bytes for padding, because it should be multiple of 8 bytes. This is a simplest heap block format. So heap block at least has this kind of form. Okay. So if you malloc, you allocate 4 integers maybe, and then 1 word is used for the header. Okay. It means the block size is not 4, it's 5, including the header. Okay. If you free, it becomes free. Okay. So this is shaded means it's allocate. This means free. White block means free. 오케이, 오늘 여기까지 합시다.